Good morning, everyone, or whatever time you're watching this. Hello. Before we jump into our probabilities, I wanted to give you another review for your final. So we're going to be finishing a truth table, so that way we're refreshing our minds on what all that entailed. We have P, Q, and R. What we want is the truth value for P or not Q if and only if R. So since we have P, Q, and R, that means we're going to have 8 values going down each column. I remember I told you to do 4 trues for the P value, 4 false, then 2 on the Q, 2 trues, 2 false, 2 trues, 2 false, and then for the R, alternate. True, false, true, false. That way we get all 8 values, all the possibilities between these 3. Now I left some room in the middle so that way we can add anything else that we want. For me personally, I'm going to add not Q, and then I'm going to add the or statement before we do the whole thing. So I'm going to pull not Q. And that's just going to negate what we have for Q. So anything true becomes false. Anything false becomes true. Then we're going to have P or not Q. So I'm going to add that one. P or not Q. And I think that's the last one we'll need. So now we're only going to focus on the column P and the column not Q, and we have an or in between. So in order for it to be true, either P has to be true, not Q has to be true, or both of them have to be true. We just need at least one of them. So I have true, false, so that's a true. True, false, true, 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 false, false. Okay, so we don't have any trues. And that's another one, false, false. False, true, we have one. False, true, we have one. Okay, so we have our or statement. And now we are able to find the value of the whole thing. So we have P or not Q, if and only if, R. So now we're going to look at the or column and the R column. And in between those two things is if and only if, the biconditional. The biconditional is true as long as they have the same value. So they can both be true or they could both be false. If they're not the same, the whole statement becomes false. So we have true, true, they're the same. False, true, they're not the same. True, true, they're the same. False, true, they're not the same. My letters are getting bigger. True, false, false, false. True, true, false, true. 1, 2, 3, 4, 5, 6, 7, 8. Okay, as long as I got all 8. And now we have completed our truth table. We've got the column that we wanted. We have the values for the entire statement. So this was chapter 3. So if you are struggling remembering how to do the symbols, how to put our truth table together, how to find the values of statements, go back to chapter 3. This weekend is a good weekend to start reviewing for chapter 3. That way, when it comes up closer to final time, you're not struggling with these things last minute. I suggest studying a little bit every day. Do your homework and then do some practice problems from the study guide. Okay, so this is going to be our last section from chapter 11, combinations, and then we're going to start chapter 12, the introduction to statistics. What I want to be able to do by the end of this lecture is solve problems using combinations. Then take a look at sampling techniques. We'll go over what is a random, systematic, cluster, stratified, and convenience sample. We'll briefly discuss the misuses of statistics. Then we'll look at diagrams. So frequency distributions, histograms, frequency polygons, stem and leaf, and circle graphs. It shouldn't be too heavy today, but it is important so that way you can build on all of our foundations today. All right, so let's finish up chapter 11. A combination is a distinct group of objects without regard to their arrangement. Remember, this is different than a permutation because permutation order matters. Combination order does not matter. So the Earth Club at Joliet Junior College has members Jasper, Carla, Opal, David, and Malcolm. Determine whether the description given below regarding a selection involving the Earth Club members describes a permutation or a combination. So our options here are the club will select a president and a treasurer, and of the 5 members, 2 will be attending the Sierra Club meeting together. So I want you to pause it. Just write down, do you think A is a permutation or a combination? Do you think B is a permutation and combination? And then why do you think that? Okay, so now we're going to go through and discuss what each of these are. So since A, the club will select a president and a treasurer, since the president's position is different than the treasurer's position, the order in which they're selected is important. For example, let's say Jasper is the president and then Carla is the treasurer. Well, that's completely different than if Carla is the president and Jasper is the treasurer, right? We still chose the same 2 people, but the order we choose them is important, so that makes it a permutation. Now, for part B, of the 5 club members, 2 will be attending a Sierra Club meeting together. Well, the order that the 2 people are chosen does not matter. I could choose Opal and then David, but that's the same as choosing David and then Opal. Both of them are still going to the meeting, so that's a combination. And this is how we will be calculating our combinations. This is our combination formula. You can see that it is very similar to our permutation formula with our n factorial on top. That's all of the options we have. The difference between n and r factorial, but we have the additional multiplication of r factorial in the denominator. And this allows us to calculate that the order does not matter in a combination. So let's use it. In your American history class, you are assigned to read any 3 books from a list of 8 books. In how many ways can you select 3 books to read? So this doesn't matter the order, you get to choose any 3. We have 8, we're choosing 3. That's how I remember this one, 8, choose 3. So 8 factorial is my numerator. I do the difference, 8 minus 3 factorial, and then that 3 factorial. So we've got 8 factorial over 5 factorial times 3 factorial. Now do not do 5 times 3 and 15 factorial. That's not what the denominator is. We're going to have 8, 7, 6, 5, 4, 3, 2, 1, and then 5 factorial and 3 factorial separate, okay? Both of them. And then at this point, I do my cancellations. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And 3 times 2 is 6. So we have 7 times 8. There are 56 different ways to read the 3 books. So you got lots of choices there. Now for some of you, you may have found the button in your calculator for combinations and permutations. That is totally fine as long as you use it properly. Your calculator is an adequate tool to use for these types of things. Okay, next we have Isaac, the faculty advisor for the Brain Bowl team and Northeast Texas Community College. Oh, it's at. For an upcoming tournament, Isaac selects a team of 4 players from 6 eligible students. How many different teams of 4 players are possible? So again, we have 6. We're choosing 4. 6, choose 4. So our numerator, 6 factorial. Our denominator, 6 minus 4 is 2 factorial times that 4 factorial. And then we have 6, 5, 4, 3, 2, 1. 4, 3, 2, 1. 2 times 1. And then I'll cancel 1, 2, 3, 4. And if you really want to, you can do 6 divided by 2 is 3. So we have 3 times 5 is 15 possible teams. Now, after the tournament, Isaac takes the team out for pizza. They order an extra large pizza and must choose 3 toppings from a list of 11 toppings. How many different 3-topping pizzas are possible? Now, it's important to remember the order doesn't matter in this situation, right? It doesn't matter if I choose pepperoni, sausage, and then, peppers. Because that'll be the same if I chose peppers first and then sausage and then pepperoni last. They all make the same pizza, so the order doesn't matter in these, so we're going to continue using combinations. So we have 11 possibilities. We are choosing 3. 11 factorial, 11 minus 3 factorial, times that 3 factorial. Okay, so we have 8. And then I guess if we wanted to, we could say 9 divided by 3 is 3, and 10 divided by 2 is 5. So we have 11 times 5 times 3. That would give us 165 different pizzas. Lots of choices. Maybe that's why they only serve pizza. Okay, at the Tokyo Bangkok restaurant, dinner consists of selecting 3 items from column A, 4 items from column B, and 3 items from column C. If columns A, B, and C have 5, 7, and 6 items respectively, how many different dinner combinations are possible? So this one, we have 3, and we're looking for the total number of choices. Remember at the very, very beginning of this chapter, we said if I have all of my options, right, total possible, is take all of the total possibilities from the first one, multiply it times all the possibilities from the second one, and multiply it times all the possibilities of the third one. That was the fundamental counting principle. So now I need to calculate how many options are in the first column, column A. Column A, it says as 5, and we are choosing 3. So A has 5, choose 3. And I'm going to multiply that times B. B has 7, and we're choosing 4. And then C has 6, and we're choosing 3. So I'm going to calculate the combinations 3 times for each column. One column has a different combination than the other column. So I have to do it 3 times, and I'm multiplying it all together because that's what our fundamental counting principle tells us for all the different outcomes. So the combinations for 5 choose 3, right? 2 factorial times 3 factorial. I feel like we may have done this one already. One, two, three. Then we have 2. 5 times 2 equals 10. And then we have 7 choose 4. Four. 3 times 2 is 6. 7 times 5 is 35. Then we have 6 choose 3. Um, 3 times 2 is 6. 5 times 4 is 20. And we multiply 10 times 20 times 35, we'll get 7,000 different dinner options. Lots of choices here. Okay, the last piece I have for chapter 11 is just a summary of all of our counting methods. This goes over what that fundamental counting principle was, and then how to calculate permutations and combinations. So you can save this for whatever you need it for. Next, we're going to go to chapter 12. So we're going to look first at 12.1, and this is just different sampling techniques and then the misuses of statistics. So, for example, before I get to an example, let's start with what is statistics. It's the art and science of gathering, analyzing, and making inferences, which are predictions from numerical information. The numerical information is referred to as the data. So if you're gathering data, you're analyzing it, and you're making a prediction from it, you're using statistics. There are 2 types of statistics. One is descriptive. That is concerned with collection, organization, and analysis. And then the inferential side is concerned with making the predictions from the data. So there's 2 different pieces of it. Both are very important to be accurate. Okay, now, when we go into collecting data and using it, there are important pieces we need to know what we're talking about. So the population is all of the items or all of the people. So if we're looking at collecting data from all these types of people, that's our population. We will refer to a subset of the population as a sample. That's what we're going to use to be making predictions concerning the whole population. So sometimes it's impossible to make a conclusion on the whole population. Like, there's no way I could ask everybody this question, but I can grab a sample and ask them and then make a decision about the population as a whole. An unbiased sample is one that replicates the whole population, whether it's income, education, gender, race, religion, political affiliation. It remains unbiased, right? And in statistics, that's probably the most important thing. Is you want to be very clear in the type of information you're gathering. And so if you're gathering information about people, then you want to make sure that it is either as clear or specific or unbiased as possible. That way you're making these statements and it's not like, well, everybody that you talked to were in college, so you didn't really get anybody that was not in college. You know what I mean? So you want to keep your sample as clear and specific as possible. Okay, let's talk about the types of sampling. So if a sample is drawn, that each time an item is selected, it has an equal chance as all the other items, that's a random sample. So if you're just, everything that you choose has the same probability of being chosen, that's a random sample. A systematic sample is where you have a random starting point and then you select every nth item. So for example, if you put everyone in one line and then you said, I'm going to take every third person, 1, 2, 3, you come in, 1, 2, 3, you come in, 1, 2, 3, you come in, and everybody that comes in is going to answer some questions. Then there's a cluster sample. This is also known as an area sample. It's usually applied to geography. So maybe you're gathering a sample of everybody that lives in a certain zip code. So that would be a cluster sample. When a population is divided in parts called strata, then that will be called a stratified sampling. So maybe you're looking at people with an income of less than $30,000, and that's your sample. Then you have a certain strata that you're looking at. And then there's the convenience sample, which is just really easy or ready to use. So maybe you're just gathering data on all the people in your class, and they're just right here. So you're just going to use it, convenience. Okay, so let's look at some of these different sampling techniques and you identify which is which. We have every 20th smartwatch coming off an assembly line is checked for defects. So which type is that? This is counting every nth one, right? So this is a systematic. A systematic sample. The $50 gift certificate is given away at the National Nurses Convention. Tickets are placed in a bin, and the tickets are mixed up, and then the winning ticket is selected by a blindfolded person. So this one, every ticket's thrown in a bin and one is chosen, so it seems like every ticket has an equal chance of being chosen. This one would fall under random sample. Children in a large city are classified based on the neighborhood school they attend. A random sample of 5 schools is selected. All the children from each selected school are included in the sample. So this one, they are classified based on the neighborhood school that they attend. So it's very geographic, right? They're going to a school based on where they live. And of that, they're choosing the schools. So because this is geographic, we're going to call it a cluster. The first 50 people entering a zoo are asked if they support an increase in taxes to support a zoo expansion. So they're just grabbing people walking into the zoo. That is very convenient. Well, I guess convenience sampling. All registered vehicles in the state of California are classified according to type: subcompact, compact, midsize, full-size, SUV, and truck. A random sample of vehicles from each category is selected. So the vehicles are divided into what we would call strata. Those different types are the strata, and a random sample from each category that would fall under the stratified sampling. Stratified sample. So hopefully that helps clear up all the types of sampling, how we are gathering the data. Now, it's very important as we study statistics that you examine statistical statements very carefully before you just accept them as fact. And what I mean is, lots of stats out there today are being used for personal gain or business gain, to sway you a certain way, and not just in class, but outside of class most of the time. You want to be very careful on accepting statistical statements. So here I have 2 questions you should ask yourself. Was the sample used to gather the statistical data unbiased and of sufficient size? You know, how many people were involved in this statistical statement? Did you only ask 5 people, or did you ask 1 million people? That would give me a better idea. Is the statistical statement ambiguous? That is, can it be interpreted in more than one way? So if I said, oh yeah, it's an average company, well, what does that even mean? Is it average size? Like, did we see that it's in an average building? Is it shabby? Is it, does that mean that their product is average or subpar? You know, like, what does it mean when I say average? Am I actually calculating the mathematical average, the mean? Or am I talking about its description? Or am I talking about its size? Or am I talking about where it is or it's located? Or so if it's something is really ambiguous, you should be careful. Here's an example. 4 out of 5 dentists recommend sugarless gum for their patients who chew gum. So first of all, we don't know the sample size. We don't know if they asked only 5 dentists and one of them said no. We don't know how many times this experiment was performed to get this result. And we also don't even get the mention that maybe only 1 out of 100 dentists even recommend gum at all. Maybe 99 out of 100 dentists say don't chew gum. And they just kept asking and asking and asking until they got 4 out of 5. So just be wary of what you read, what you hear, unless they give you all the information about it. Here's some more. This is a visual. And just take a look at stock A, stock B. You can see that it's over 6 months. We can see the price is on our vertical, so showing us. Our natural instinct is to say, wow, stock B is doing so much greater than stock A. Look at that growth. But in reality, these are representing the same information. Both of these tables are representing the same information. One is just zoomed in. So very misleading. Here's another where we have data from 2018 and 2019. Again, A looks like, wow, look at how much growth there is, and B looks like, wow, it hardly grew at all. They're representing the same data. It's just zoomed in. So when you are given visuals of data, be wary. Know what you're looking at. Interpret it correctly. You know, read what is the data even telling me. I can see one of them goes from 95 to 100. Well, yeah, it looks like a lot of growth, but it's only showing me 5. So just be aware. Here's the last one. Circle graph. Why people surf the web. Top 6 reasons Americans say they use the internet. Gathering information, research, checking the news, surfing for new sites, using their email, or making purchases. So it looks okay. Just by glancing, we see what each piece represents. We see the percentage of the pie that it takes up. But it's misleading because all of these percentages add up to over 100%. So we always want our circle graphs to add up to 100%, and this goes overboard. This is over 100%, so I don't even know how it, like, what it's representing. So, yeah. Now we're going to move into the area where you're going to be creating diagrams. So you don't want to create misleading information on yours. So we'll look at a few. The first one is called a frequency distribution. This is a list of observed values and how many times they happen. So every piece of information you get is a data, and then if you keep track of the data, you'll, like, a frequency distribution usually is just like a tally chart. Like, okay, I'm gonna spin this spinner and it's gonna land on red, blue, yellow, or green, and every time it lands on one, I'm gonna keep track of how many times it lands on red and how many times it lands on yellow. That's our frequency distribution. So here's an example of one. This is the number of children per family recorded for 64 families. Let's construct a frequency distribution of the data. So we can see we have 0 children, 1, 2, 3, 4, 5, 6, 7, 8, and one family has 9. So what we do is we list out all the values that we see. So we have the numbers of children, we have 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. And then we'll keep track of how many times we see those numbers, so number of families. So how many times did we see 0 children? 1, 2, 3, 4, 5, 6, 7, 8. How many times did we see 1? 8, 9, 10, 11. How many times did we see 2? 18. 3 is 11 again. 4 is 6 times. 5 happened 4 times. 6 happened 2 times. 7 happened 1 time. 8 happened 2 times. And 9 happened 1 time. And if we add those all up, we'll get back to all 64 families. And that's it. That's our frequency distribution, is how frequently did the data happen. So here are some rules for data if we group them by classes. And a class just shows us that, okay, instead of going one age at a time, maybe I say, okay, families with kids from 0 to 4. Families with kids from 5 to 9. So we start making bigger groups. Maybe we have lots of data to get through, so we start grouping them together. That's called the class. The classes should be the same width. We can see here 0 to 4, 5 to 9, 10 to 14. They're all the same width, right? The classes should not overlap. So I don't go from 0 to 5 and then from 5 to 9 and see a 5 in both. They're each cut off. They don't overlap. And each piece of data should only belong to one class. So someone can't fall into 2 different classes. These lower limits are called the lower class limit. And then we have the upper class limits as the highs. Okay. Let's look at this one that has classes. So the table that we see, it was a huge table, shows the number of copies sold for the 30 top-selling novels of all time. The number of copies sold is rounded to the nearest million. Construct a frequency distribution of the data, letting the first class be 50 to 94 million. So, using 50 to 94 as our first cutoff, now we can make all the other classes match. So we'll have copies. And then number of novels. Okay, so it says the first class needs to be 50 to 94. So all of the rest have to match. And it looks like the highest we're going is... The highest is 500. So let's split them off. 50 to 94, and then 95 to 139. That way they have the same width. And then 140 up to 184. 185 up to 229. 230 up to 274. 275 up to 319, 320 up to 364, 365 up to 409, 410 up to 454, 455, we're getting so close, up to 499. And then we have to make one whole new class for the last one, because there is one that's 500. So 500 at 544. Okay. Now we'll put how many we see in each class. So in between 50 to 94, we go through and find how many fall under this 50 to 94 category. Okay, we have 21. And we keep doing 95 to 139, there's 5, 2, 1, and then there's a big gap all the way to 500. So we've got 0, 0, 0, 0, 0, 0, and then one of them falls in there. And that will be our frequency distribution with the classes. So the modal class, if we want to look specifically at how these classes break down, the modal class of a frequency distribution is the one with the greatest frequency. So in this case, the modal class is the 50 to 94. There were 21 in that one. The midpoint of a class, also the class mark, is the lower and upper limits added and divided by 2. So it's a lot like when we found the midpoint. So you add 50 plus 94 and you divide it by 2. That would be the midpoint of that class. Here's a frequency distribution of family income. So we have in thousands of dollars, rounded to the nearest 100, 15 random families. Let's construct a frequency distribution. The first class is going to be 31.5 to 37.6. So pause it, try it, and then we'll do it. Okay, I'm going to put income and number of families. So we have the first class, it says to make it 31.5 to 37.6, and then we'll go to the next 37.7, add the same amount, 43.8, and then we'll go to the next 43.9, and we'll add the same amount, 50, and then we got 50.1, and we'll add the same, 56.2, 56.3 up to 62.4, 62.5 up to 68.6. Okay, so now we'll just go through and find how many times they fall into each of these categories. So I see 2 that fall in this one, 3 that fall in this one, 5 in that one, 3 in that one, 1 and 1. And that's our distribution. Next, we'll look at histograms. A histogram is a graph with values on the horizontal and how many times they happen on the vertical. And then the frequency polygon is just a line graph. So histogram uses bars, frequency polygon uses lines. So let's make a histogram of this frequency distribution. So first I'm going to make my graph. Okay, and we have the number of children going across here. And the number of families, so how many times we see that happen. Okay, so the number of children goes from 0 to 9, so I'm actually going to label 0 on here. And then the number of times that they happen, it looks like it goes from 1 up to 18. So if we just max it up at 20, that should cover everybody. Halfway is 10, 5, 15, something like that. Okay, so how many got 0? We have 8. And then 11. 2 is 18. 11 again. 6. 4. 2. 1. 2. 1. Very messy, but you get the idea where it's just making bars. Let's see, I thought I could you can fill them in if you want, and that's how our histogram will be, is just filling in the data for each of these items. So we're putting it from table form into graph form. Okay, let's construct a frequency polygon. So remember, this works the same way, but instead of using bars, we're going to use lines. So this one, we have the number of children, going from 0 to 9. And then the frequency, the number of families, is going to go up to, I'm just going to max it out to 20, right? Same setup. Okay, so at 0, we had 8. And then 1, we had 11, 18, 11, 6, 4. 2, 1, 2, 1. And then once you have your dots, we just go through and connect. And I'm going to start from 0, 0, like zeroing it out, and then we'll go up to here, to here, And notice you don't make them curve through the dots like we do with a graph. We go from point to point and make it a nice, nope, a very straight from point to point. So it's like a jagged graph. And that is our frequency polygon, except for this guy. Oh. There. And I guess we can make this go down to 0, too. Okay. Okay, construct a histogram of the one-way commuting distances for 70 workers, and then a frequency polygon. So we're going to just lay these on top of each other. And we have the distance in miles. And the number of workers. So we'll have the distance, let's see. Well, I'm going to start with the number of workers. 25, 20, 15. Okay, we'll do that. And then let's see, how can we break up? What I'm going to do, since each of the distances is a class, I'm going to find the middle of each class. So the middle of 1 through 7, if I add 1 plus 7 and divide by 2, that's 4. So we'll put 4. And then the next class, I'll just put the middle. Between 8 and 14, we'll put 11. The next class, we'll put the middle, 18, 25, 32, and 39. So this one was 15. This one was 24. This one was 13. This one was 8. 5 and 5. So our histogram, go up to that point and make a bar. But we also want the frequency polygon, so we'll make our straight line segments going from point to point. There we go. And they're just on top of each other like that. And here's another one that you can do. Construct the frequency distribution from the histogram, showing the airport luggage. Works the same way, you can get extra practice. Okay, let's look at a stem and leaf display. We have a way to organize and group data that allows us to see all the values, and that's our stem and leaf. So we'll go through, here's some data, 20 visitors at the national park. Let's use a stem and leaf. So the first thing I do is I go through and I find all of the beginning values. So 2, 6, 4, 7, see all the beginning values. And those are going to be listed first. So our lowest one is a 2, 3, 4, 5, 6, 7, I think it's our highest. And then we'll put on the leaves. So we'll put 29, 29, 31, 39, 43, 56, let's see. Move this guy over. We have a 32, 44, 44, 45, 47, 27, 28. And this is how we would make our stem and leaf. We got 50, 50, 56, 58, 59, 60, 62, 68, 71, 72. All right, that's our stem and leaf plot. And last, we have circle graphs. You may have already learned about them as pie charts. They compare parts of one or more components to the whole. Here we have the data of 800 people who attended a circus and were asked their favorite performance. The circle graph shows the percentage of respondents that answered tigers, elephants, acrobats, jugglers, and other. Determine the number of respondents for each category. So we had 800 people total, and each of these is a percent of the total. So of always means multiply. If I start with the tigers were 38% of the 800 people. So we have 0.38 times that 800, which tells us there were 304 people that loved the tigers. And we'll just go around the whole thing. Elephants. .26 times the 800. We get 208. The acrobats. 17. 136 people. The jugglers. 0.14 times 800 gives us 112. And other. These are the people that probably like the clowns. 5%. 40. And if we were to add up all of the people, they take us back to 800 total. Okay, so make sure this week you get your biblical worldview done. Get it done right away, because Friday you're probably not going to remember to do it. Just do it right away. Turn that in. Your homework, we did 11:8, 12:1, and 12:2. Those are due by Sunday. They are not difficult, so you can get those done pretty easily before the weekend, and then have the weekend to be with family. And then, like I said, make sure you're studying for your final. I would work my way through a few practice problems in chapter 3 to be prepared.